These notes are over the law of conservation of energy. And so if we considered a closed system, okay, so for example, if a classroom was a closed system, no amount of energy is going to be able to come into the classroom and no energy is going to be able to leave the classroom. Okay, so all the energy that exists in the classroom would have to be converted in order to continue or sustain. Okay, so it's just transferred around. So energy cannot be created or destroyed. It's only transformed from one form to another. And we kind of talked about the different ways that energy could transform before. So mathematically, it just means that the total initial energy has to equal the total final energy. Okay, so typically situations involve just a change in height and velocity. So we can write out a specific version of this equation where we have the initial kinetic energy plus the initial gravitational energy is going to be equal to the final kinetic energy plus the final gravitational energy. We'll find also that we can have a change of kinetic energy is equal to negative, and generally I want to put in parentheses, negative change in gravitational energy. Okay, and just as a reminder, for kinetic energy, it's 1/2 mv squared, okay, or we have the 1/2 m and then parentheses v2 squared minus v1 squared. And then remember that change in gravity is going to be mass times the gravitational constant times delta H, or change in height. Okay, so for the first example here, a diver slips and falls off a diving board. If the diving board is 10 meters high, what's the diver's speed right before he hits the water? Okay, so just to draw out our diagram, if I have my person here who is standing on the diving board that is 10 meters high. Okay, this is going to be our height, okay, or a delta D. Here is the water, right? Here's my diving board. Okay, so at this point here, because the person is not moving to begin with, their initial kinetic energy, so kinetic energy I, is going to be 0 joules, okay? And then once they actually hit the water, okay, our water is our low point, so this would be considered our final gravitational energy of 0. The total initial energy has to equal the total final energy. And so our initial energy would be made up of our initial kinetic plus our initial gravitational. And it's got to equal our final kinetic plus our final gravitational. Okay, so we just stated that our EKI is going to be 0, right? And then also our EGF is 0. All right, so we're just left with EGI equals our EKF. So plugging in the formulas that we know for each, for gravitational, remember it's going to be mass times the gravity constant times our height, and this will be our initial height. Okay, and that's going to equal 1/2 mass times our final velocity, which is what we're trying to find. Okay, so if we get VF by itself, if I divide over the masses are going to cancel. Okay, and then divide over the half, it would become 2, and then take the square root. I'm going to get the equation 2GHI equals my VF. All right, so plugging in the information, 2 times 9.8, which is my gravitational constant, times the initial height, which was 10, is going to equal our VF. And so we'll find that VF is 14 meters per second. So if we kind of examine this diagram here, the person has the greatest amount of gravitational energy because they're the highest off the ground. They have the most potential to do work, meaning that remember, doing work has to do with displacement. So they have the most ground to fall, okay, or the most distance to fall from this height. Okay, so here's where they have the greatest GPE. Okay, but their kinetic energy was 0 because they were not moving. Here at the bottom, this is where their kinetic energy is going to be the greatest because they've been accelerating towards Earth. Okay, so our kinetic energy is going to be the greatest down here, but our gravitational potential energy is going to be 0 because they've hit the water. They're not going to continue to fall. So if we look at the total amount of mechanical energy, both kinetic and potential, it's going to stay constant. So like I just explained, on the diving board, the energy was all gravitational potential. At the bottom, energy was all kinetic energy. Okay, so if I were to kind of fill it in, at the top, all of our energy was kinetic energy. Okay, at the bottom, gravitational. At the bottom, all of it was kinetic energy. Okay, so it converted from one to the other. Okay, but it was still equal to the total energy, which is that last bar. So in between the top and bottom, the total energy is a combination of both kinetic and gravitational potential energy. Okay, so as my person was falling down towards the water, okay, their GPE was decreasing as their kinetic energy was increasing. Okay, so if we have an example, a 73 kilogram skier is at the top of a 65 meter high hill. The skier is stationary to begin with, then slides down the hill to the bottom. Okay, so first off, what's the total energy of the skier? And then secondly, how fast is the skier moving at the height of the hill? Okay, so first, let's kind of just draw out our picture. So we have our hill. Our hill is 65 meters. So here is our person at the top. Okay, once again, their kinetic energy here. Oops. Their initial kinetic energy is 0 here because their velocity is 0. They're not moving. Okay. And then at the base, this is where our kinetic energy is going to be the greatest, but our height here is going to be 0. Thus, our final gravitational energy is 0. Okay, and then we have the halfway point, which is what they'll ask us. And so half of 65 would be height of 32.5 meters. So I've kind of went ahead and set up this problem. I'm actually going to make this, replace this with question number 1. Okay, we're going to do question 1 that's in your actual practice as the example, and then this will be part of your homework that you turn in. Okay, so I kind of helped you set it up. So we're going to continue on to the next one, but this will be part of your homework as well. Okay, so for question number 1, a student is swinging a 200-gram yo-yo on a 1 meter long string. How fast must the yo-yo be moving at the bottom of the circle to reach the top of the circle with no speed? Okay, meaning that it's slowed down so much that it kind of stalls out at the top. So first let's draw the diagram. So if I have my yo-yo, okay, which has a mass of 200 grams, which we would need to convert to kilograms, but we'll find that the mass is irrelevant because they'll actually cancel out. And it is going in a circular path, well, about as circular as I could draw it. And so this is 1 meter long, okay, so from the bottom to the top, it would be a total displacement or total height difference of 2 meters. Okay, so up here, it wants it to have a speed or velocity of 0. Thus, it wants the final kinetic energy to be 0. Okay. And then down here at the bottom, our height would be 0. Thus, our initial gravitational energy is going to be 0. Okay, we want to figure out what is the velocity here, because this will be where our kinetic energy is the highest. Okay, so for this one, we're going to use the equation change in kinetic energy is equal to the negative change in gravitational energy. Okay, so change in kinetic energy would just be EKF minus EKI equals minus EGF minus EGI. Okay, so we already found that EKF is going to be set equal to 0 and EGI is going to be set equal to 0. So EKF will be 0 and EGI will be 0. Okay, so we're left with negative EKI equals negative EGF. So our negatives are actually going to cancel out, okay, and be dropped off. So plugging in the equations for each, for kinetic energy, we're going to have 1/2 and 1/2 mvi squared equals our gravitational final height, which is mg GH, and final height. All right, our masses are going to cancel out. And then if I'm trying to get velocity, the initial velocity by itself, I'm going to have VI equals the square root of 2GHF. So plugging in the information, we have 9.8 as our gravitational constant, and then the height, the total height, or the ending height will be 2 meters. So we'll get that VI, or the velocity at the bottom, would be 6.26 meters per second. So, like I stated before, you will be finishing up question or example number 2 as your practice homework. So doing part A and part B, what's the total energy? So finding the total initial GPE would tell you the total energy in this problem. Okay, so you can calculate what is the GPE of the person at height 65 meters above whenever they are starting stationary at the top. Okay, so having an EKI of 0. For question number 2, it's going to be utilizing the equation that we just used for the practice question 1 up above. So using and I'm going to write out the expanded form, but the EKF minus EKI equals negative EGF minus EGI. Okay, so the initial point for all of the ones that you're going to be calculating is going to be point D. Okay, so then you're just subbing in all of the final values with the different A, B, C, and E. For question number 3, you only have to do the boxes that are on the left. Okay, so you do not have to do utilizing the kinematic equations. It's just to show you how they're related and you will get the same answer, but I just want you to focus on the utilizing the equations that we have for the conservation of energy. And then for question number 4, this will be very similar to the problem that we did, the very first problem that we did, where you'll use the total initial energy is equal to the total final energy. Okay, the only difference is that you will be calculating or finding a different variable, so we are finding height, so you'll have to basically plug in all of the information that you have and then solve for the final height. Where your speed, your velocity, would be 15 meters per second. Okay, and then you do not have to do question number 5.